Where we're in the lecture notes. So we're in chapter 4 already, on page 23, on the binomial distribution. So remember what we were talking about yesterday at the end of the lecture was the notion of special probability distributions for random variables. And we're focusing on the case of a one-dimensional random variable x, which is in a discrete state space. So we talked about a couple of distributions. So let us remind ourselves what they were. So the first one was the notion of a Bernoulli random variable. We did the uniform, but we'd already seen that before. So the Bernoulli distribution, remember, was the notion that you have a random variable x, which could either be 0 or 1, and it's 0 with probability 1 minus p and 1 with probability p. So it's called a Bernoulli distribution as it corresponds to a Bernoulli trial, which is an event which has an outcome which is binary, i.e. a success or failure, 0, 1. 1, 0, in fact. Okay, so we were talking about this Bernoulli distribution. And then what we were thinking about is the notion that we take a collection of n independent and identically distributed Bernoulli trials, and we count the number of successes in those n independent and identically distributed Bernoulli trials with success probability p. Okay, so p is this parameter here. And we were saying that basically in this scenario, the chance to get x successes from n trials is going to be n choose x times p to the x times 1 minus p to the n minus x. So that's the binomial distribution. So this thing here, this is our binomial coefficient that we've been seeing for the past few weeks. Okay, and so we're reminded that basically the definition, if you like, of a binomial distribution, is essentially this. So x, the binomially distributed random variable, is equal to a sum of independent and identically distributed Bernoulli trials. So x1 plus x2 plus dot 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 plus xn, and these xi's are Bernoulli with success probability p and independent of each other. Okay, so we talked about the derivation of this probability mass function like this. We talked about that, and where it applies and when it doesn't. Okay, and we'd reached this distribution, this result, which was to derive the variance, or as a result on the mean and variance of a binomial distribution. So basically the expectation of x, as you can see in the second bullet point, was n times p, and the variance is n times p times 1 minus p. And we had discussed about the scenario of how to compute these things, and we've shown that the direct computation of the expectation is not trivial. I mean, you have to do some work. So what we're going to do now, before we go any further, at least we're going to spend a little bit of time understanding this result. So these are some new lecture notes. We're just they're on alumni, whatever you call it. And basically, I'm just going to show you how you can compute the mean and variance of a binomial, the easy way or the easier way. So remember what we did yesterday is we used the definition for expectation to compute the expectation of a binomial random variable. We didn't compute the variance. It can be a bit tedious to do it that way. So basically what we're going to do, I'm just going to show you this. These are kind of external to the lecture notes. So in some sense, you won't have to worry about this coming up in the exam. But let me just tell you how you can compute the binomial mean and variance of the binomial. Okay. So just a couple of results which we have seen kind of already, but let me just recall for your benefit. So suppose that what we have is a sequence of real valued random variables x1 up to xn with finite means. So these random variables can be dependent, independent. There's nothing that we need to assume other than the fact that they have finite expectation. Then what we have seen in lectures already is the expectation of the sum of these n random variables, little n is known, there's no stochasticity, is equal to the sum from I is 1 to n of the expectation of each of those random variables. Okay? That basically follows because integration or summation is a linear operator, if you like. I mean, if that helps you. So that's the first result. We're going to use that in a moment. That is easily going to allow us to derive the mean of a binomial. Okay, the variance will be a little bit more difficult. So we just remember or recall the following results, and I think it shouldn't be in the lectures actually, but let me just tell you about this. So if you have a sequence of real valued, independent, so it's critical that we need independent, random variables, x1 up to xn, and they have finite variances, okay, because I'm going to compute the variance, so I want to have finite variances. Then the variance of the sum I is 1 to n of the xi's happens to be the sum of the variances. I is equal 1 to n of the variance of each random variable xi. Okay. Critically here, of course, all these variances on the right-hand side of that equation must be finite for these things to make sense. And they're important that they are independent, because this result does not hold necessarily for dependent random variables. Okay, let me just show you why that's the case. It will give us a chance to do some simple calculations. So how do you work that out? Okay, so just it's a little notation. So I just denote by mu subscript I as the expectation of xi. Okay, that's just going to make my life easier. I don't have to keep on writing it down. So now I want to compute the variance, so I use the definition. So the variance of any random variable, here the sum I is 1 to n of the xi's, it's a scalar, is simply the expectation of that random variable, take away its mean, all squared. Okay, that's by definition. So we know that the expectation of the xi's is the sum I equal 1 to the n of the mu i's, just by using this result. Okay, so the mu I is defined like this. I have the expectation of this is the sum of the I is 1 to n of the expectation of xi's. The expectation of xi's are mu I. Okay, so that's just the definition of this variance formula that you see towards the bottom of the slide. Okay, so now how do I compute the variance of this? Okay, to compute this, now the variance of the xi, so this, the sum I is 1 to n of the xi minus the sum I equal 1 to n to the mu I is the same as the sum I is 1 to n, and I just difference each consecutive pair. So this difference here is just the same as this thing here. Okay, and so the variance is basically equal to this thing all squared. So this is that what you have there. Okay, and now all I want to do is I want to compute the expectation of the sum of random variables all squared. So the sum of n terms, and I square it, is just the sum of the square of the terms plus the double sum over all pairs not equal. Okay, so this is just, so if you think of this as xi minus mu I as being a point ai, then the sum I is 1 to n of the ai all squared is just the sum of the ai squared plus the double sum over all pairs I and j, which are not equal, of ai times aj. Okay, that's a general result. There's nothing to do with probability there. Okay, like I say, you're never going to have to do these results in an exam, but you may be curious as to why this result is the case. So I'm just telling you, also because we're going especially fast. Yeah, so I just want to slow the lecture down a little bit. Okay, very good. So now what do I do? So now we know the expectation of a sum of random variables is the sum of the expectations. So I can take the expectation of the sum of these two is the sum of the expectations, and I can take those summations out. Okay, so I just get the sum I is 1 to n of these ones plus the double sum over all i's and j's not equal of the expectation of this product. Right, but the key point is that the pair of random variables xi and xj, I and j are not equal, are independent. So the expectation of their product is equal to the product of their expectations. Okay, that's a result that we have seen earlier in the course. Okay, now what do we do? Well, the key point is, remember that we have said from the beginning that mu I is the expectation of xi. Okay. So if I look at this term, the expectation of xi minus mu I, that's equal to 0 for any I, and respectively this is obviously equal to 0 for any j. So this entire term here is 0. Okay, so that gives us this. Okay, so we've got the sum I is equal 1 to n of the expectation of xi minus mu I all square. Well, this thing, this is by definition the variance of the ith random variable. So then we are left with the result that we wanted to conclude. Okay, so just in case you're wondering why it's the case that for independent random variables, the variance of the sum of random variables which are independent is equal to the sum of the variances, that's a verification. And they have not used anything more complicated than in the independence along the way. Okay, so that's all very exciting. So now what I'm going to do is I'm going to verify this theorem that we have stated in the lecture course. Okay, so basically now what we want to do, so we have x is binomial np. Okay, so we know, that's one of the things that we stated earlier today, that if x1 are IID, that is independent and identically distributed, so these x1 up to xn are independent random variables, they're all independent of each other, and they have the same distribution. And they're Bernoulli random variables with success probability p. And we also know that I've said earlier that x is the sum I is 1 to n of the xi's. Okay, so if I want to compute the mean and the variance, I can use the two results that I've done already. Now note that the xi's, one of the results that we did yesterday, and I stated it in the lecture, that basically, the mean and the variance of a Bernoulli was like this, and these are easily calculated because the expectations are just sums over two numbers. Okay, so this is how you can calculate this one. Okay, so we know the mean and variance of a Bernoulli random variable. So the expectation for any I of xi is p, and the variance for any xi is p times 1 minus p. So now if I want to compute the expected value of a binomial random variable, the easiest way is to proceed as follows. The expectation of x is the expectation of the sum I is 1 to n of the xi's. Okay, and we know from this result up here, the expectation of the sum I equal 1 to n of the xi's is this. So the sum of the expectations. Okay. And now we know for each I, the expectation of xi is equal to p. Okay, so I just substitute for p inside here. And so this is just p, but I'm adding p together n times. So the expectation is n times p. Okay, so that's the easiest way. You can see just a few lines of calculation. There's not really much work to be done. The variance is, again, very similar. It's one line. The variance of the random variable x, where x happens to be Bernoulli distributed, is the variance of the sum I equal 1 to n of the xi's. But we know, again, this is the thing we were just talking about, that we have this equation. The variance of the sum I equal 1 to the xi's is equal to the sum of the variances. The xi's are independent. Okay. So we have this equation here. Now we know, as I said earlier, the variance for each I of xi is p times 1 minus p. Okay, and this is the same for each I. So p times 1 minus p is summed n times. So I have n times 1, p times 1 minus p, or npq as is stated in the lecture notes. Okay, so that's where, or what is the expectation. So you can see that there's a little bit of work to be done, but this is much easier. When I say easy, you still have to do some work, but it's much easier than going straight to the definition. Okay, very good. So that's just, it's just, just to show you that these results, they're not really out of your reach. I'm not sure why they're not, these proofs are not here, but anyway, we put them in the notes. I put them down for you. I'm not going to ask you anything about that in the exam. These calculations are perhaps slightly hard for this course. I'm just trying to illustrate things for you. Some of you who are more mathematically inclined might be interested. Okay, and we had said this already. Okay, so now what we're going to do is we're going to look at some examples associated with binomial distribution. Okay, and these are all kind of fairly trivial. I'm not sure how much you'll learn from them, but anyway, let's learn about them. Anyway, so we've got flipping a fair coin, presumably, and we want to ask the probability of observing 6 heads of an unbiased or fair coin when I flip it 10 times independently. Okay, so this is not so difficult, and there's one way to do this. So if we denote x as the number of heads in those 10 independent flips, okay, we know when we flip a coin we have 2 outcomes, heads or tails. We encode success as heads and tails as failure. Then we have a collection of 10 Bernoulli trials which are independent and identically distributed, and the success probability is precisely 1/2 because it's a fair coin. Okay, so we're going to say, or we make the statement, that x is distributed as binomial, n is 10 and p is 0.5. Okay, and now we have this formulation. Okay, we are going. Of course, there are some assumptions here. We're assuming that the trials are independent, but that's life. You have to make some assumptions sometimes. And we want to now compute the probability of getting 6 heads. Okay, it's pretty straightforward because all I have to do, I have to substitute x is equal to 6 into our formula. So we have the formula here. I have n is 10, I have p is 1/2, and x is 6. So I'm just calculating, substituting numbers into a formula, right? So I have to compute 10 choose 6 times 1/2. Well, in fact, it's going to be 1/2 to the power 10 actually at the end. in this case. And that's what you get. And it's 0.2051. So that's the answer to this one. Okay, you can do it a different way. I can't imagine why you would ever want to do it this way, but if you like, you could, because we know that the probability that x is equal to 6 is equal to the probability x is at least 6 minus the probability that x is at least 7. Okay, and these numbers you can get from a table, so I presume that they were supposed to be a link to a table of probabilities, but which basically corresponds to these CDFs here. Well, they're actually called survivor functions, but anyway. So you could do it that way. I mean, in this particular case, you would never do it this way because this formula is very explicit and it's very simple to calculate. Okay. In fact, these days, you would never even use a table. You don't use tables these days. You can get, for any standard statistics package, can calculate this for you. Just very simply. There's no need for tables these days. Okay. So let's have a look at example 2. So basically you're given the following. The probability that a child recovers from a certain kind of disease is 0.2. It's a pretty bad disease. Okay, and now you've considered 20 children. They have the disease, and somehow independently we know whether they may or may not survive the disease. So we're asked two questions. We're going to assume they're independent. That at least 8 survive and from 2 to 5 survive, inclusive. Okay. So let's think about part A. So of course we're using the binomial distribution, so that's what we're going to do. So we denote by x, the random variable, which is associated to the number of children out of the 20 which recover from the disease. And if we assume that the survival or not, so survival is assumed the success, so the survival occurs with probability 0.2, and if you consider these as 20 independent Bernoulli trials with success probability 0.2, then x is going to be distributed as binomial 20 0.2. Okay, it's not a direct corollary of the question or the statement that x is binomial 20 0.2. It is a formulation. We're making a formulation. We're making assumptions explicit in our calculation here. So if you don't assume that the survival or not of children is independent, then there's something else going on. And at this stage of our education, we don't know how to do that. So we're going to stick with the collection of Bernoulli trials being independent. Okay, so now what do we want to do? We want to calculate the probability that at least 8 survive. So that means that I want to calculate the probability that x is greater than or equal to 8. So what is that equal to? That's the probability that x is equal to 8 plus the probability x is equal to 9 plus the probability x is equal to 10 plus the probability that x is equal to 11 plus ... plus the probability that x is equal to 20. Okay. Now, of course, you would never do that on a calculator. Maybe when I was a student, not even when I was a student, maybe when I was in school, I might do that with a calculator. But you don't do that with the calculator this day. You can put that into the computer. You can tell it that the binomial has 20 trials and success probability 0.2, and it will compute that probability for you. Okay. I mean, you will never be asked by me to calculate this probability by hand. It is really, really, really boring. Okay, but hopefully you understand that this calculation is just the probability x is equal to 8 plus the probability x is equal to 9 plus the probability that x is equal to 10 ... plus the probability that x is equal to 20. Okay, part B. Part B asks us, what is the chance that between 2 and 5 survive? This one's slightly easier. So the probability that x is between 2 and 5. So there's one way, the kind of easiest way to calculate it. The probability x is equal to 2 plus the probability x is equal to 3 plus the x is equal to 4 plus the probability x is equal to 5. That's the answer. If you like, you can, as before, just compute the probability that x is less than or equal to 5 minus the probability x is less than or equal to 1. That's basically the calculation with the CDFs that we saw maybe 2 weeks ago. This probability is 1 minus the probability x is greater than or equal to 6. This probability is 1 minus the probability x is greater than or equal to 2. Okay, so these 1s will cancel, and this 2 goes first and this 6 goes second. Presumably in this table, which I don't have access to, these numbers are available in the table. Okay, but if you like, you could also just calculate the probability x is equal to 2 plus 3 plus 4 plus 5. Okay, that would be alternative. Okay, so that's example 2. Example 3, which I find slightly confusing actually, but anyway. So there's an individual who claims that they have ESP, extrasensory perception. So that's somebody who claims that they know something that we don't, or I don't at least. And basically this person is tested. So you flip a coin 10 times and then you're asked to predict it. So his ESP allows him in this case to guess which way the coin is going to land. Okay. So I don't know if any of you have seen Ghostbusters. The old Ghostbusters, that's like the start of that movie. The old one, not the new one. Anyway, sorry. I'm showing my age now. So, what you want to do, so what happens is that this individual happens to get 7 coin flips correct, which out of the 10, which is pretty high, you would think, if you've got a fair coin. Okay, now the question is, if the person had no ESP, what would the chance that he happens to get 7 out of 10? Okay, so this is a kind of a funny question, but the key point is you've got a fair coin, you flip it 10 times, and the question is what's the probability that x equals 7? And that's pretty much what it's asking. It's a bit confusing in the beginning. So this is the answer. So the question is the following. So if that individual has no extrasensory perception, then the probability that he gets it right as a coin flip is 0.5. He doesn't know, he's just guessing. So the number of correct guesses out of that 10, well, that's basically a collection of independent and identically distributed Bernoulli trials with success probability at half. So we're modeling the case where this individual has no ESP as a binomial random variable with 10 Bernoulli trials and success probability 0.5. Very good. So now all we want to do is to calculate the probability that x equals 7. Okay, so that's 10 choose 7, 1 over 2 to the power 10. Okay, is 0.1172. Okay, so what does that say? Well, the conclusion that you can look at the alternative is pointless to do it another way. But the conclusion is that basically the chance of that actually happening is quite small. So on the basis of this single trial, you might think that this person might have ESP, of course. That's if one believes in that at all. If you like, and again, like I say, there's no reason to do it this way. You can also use this CDF type method, the probability that x is greater than or equal to 7 minus the probability x is greater than or equal to 8, and you would need a table to calculate this. We don't have that right here. Okay, so I think there are 5 examples here, but this is the 4th one. Now we suppose the following, that we have 20% of all copies of a particular textbook fail a certain binding strength test. Okay, so 20 copies of the textbook were randomly chosen. Okay, and we're asked the following: well, let's start with the first one. It's such a long word. Find the probability that at most 8 copies fail the test. Okay, and we'll talk about B in a moment. Okay, so the solution, or one way to approach this, denote X as the number of copies among 20 randomly selected copies that fail the test. Okay, so the book is given this strength test, and they fail with probability 0.2, and they succeed otherwise with probability 0.8. And we're going to so failing the test is the success in our case. So if we assume that everything is independent and so on and so forth, as we have done already, then the hypothesis is that X has a binomial distribution, and there are 20 trials because there are 20 books, and the success probability is 0.2. So now answering the question is relatively straightforward, because now we want to find the probability that X is less than or equal to 8, and we want to find the probability that X is equal to 8. Okay, so the probability X is less than or equal to 8, so there are a couple of ways you can do that. That's the probability X is equal to 0, plus the probability X is equal to 1, plus the probability X is equal to 2, plus ... plus the probability X is equal to 8. Or if you like, you can say that's equal to 1 minus the probability X is greater than or equal to 9, because this event, if you like, is the complement of this one. And if you have a table which tells you what this number is, you can get that. Okay? Or if you like, you just add those 9 numbers together that I just stated. And part B asks us to compute the probability X is equal to 8. I don't know why you do it this way. The probability X is equal to 8, you just compute the formula. We go all the way back to our formula for the binomial distribution. Here, n is equal to 20, p is equal to 0.2, and x is equal to 8. You just substitute the numbers into the formula. And if you do that, I suppose the answer comes out to be 0.0221. It's a very small chance. Okay, example 5. So example 5, you have an electronics manufacturer and they claim that at most 10% of its power supply units need servicing during the warranty period. Okay. So we want to investigate this claim, and technicians at a testing laboratory purchased 20 units, and subject each one to an accelerated testing to simulate the use during the warranty procedure. I don't know how that works, but there's some way to do it. So we suppose P is the probability that a power supply unit needs repair during the period. Okay, the proportion of all such units that need repair. Okay, so this is takes a bit of time. The laboratory technicians must decide whether the data resulting from the experiment supports the claim that the chances of this failure is 0.1 or less than or equal to 0.1. Okay, so for those of you who might be interested, this is a kind of precursor to the notion of hypothesis testing, which we will discuss in the final chapter of this course. But anyway. So let's suppose the following. So we denote by X the number of units among those 20 sampled that need repair. Okay, so X is assumed to be binomially distributed with 20 units, and the probability that they need that servicing is P. Okay, so why is that the case? He's asking the question. Well, basically, each time you put this unit through a stress test, so this is what this says here. They put the thing the unit into a test, and then with probability P, you need to service the machine within the warranty period. Okay, and that's done presumably independently. So the hypothesis is this is 20 collections of independent and identically distributed Bernoulli trials. Okay, so that's Y, and the probability that they fail is P. Okay, so we now consider the following decision rule. We reject the claim that P is less than or equal to 0.1 in favor of the conclusion that P is bigger than 0.1 if X is at least 5, excuse me. And we can consider the claim plausible if X is little less than or equal to 4. So what does little x represent? Little x represents, in their testing, the number of electronic components, whatever the thing was, that have failed. Okay, that's what this thing means. I basically, it's the realization of this experiment, the number of the things that failed. Okay, the probability that the claim is rejected when P is equal to 0.1. Okay, so if you assume that P is equal to 0.1, right, then you compute the probability X is greater than or equal to 5. Okay, what does that mean? Well, that means that you compute the 1 minus the probability X is equal to 0, plus X equal 1, plus X equal 2, plus X equal 3, plus X is 4. Okay, that's the probability X is greater than or equal to 5. Okay, when N, the number of trials on our Bernoulli binomial distribution, is 20, and our success probability is 0.1. So if you compute that number, you get 0.0432. And that's an incorrect conclusion. That's the chance of an incorrect conclusion. The probability that the claim is not rejected if P is 0.2, a different type of incorrect conclusion. Okay, so if you say P is 0.2 and you get less than or equal to 4, remember this decision rule. It's all dependent on 5 and 4. Okay, so in this case, it's plausible that it's 0.1, 0.2, if you get less than or equal to 4. So here you go bigger than 0.1 in this case. Okay, so the probability X is less than or equal to 4. The probability X is equal to 0 plus X is equal to 1 plus the probability X is equal to 2 plus the probability X is equal to 3 plus the probability X is equal to 4. If P equals 0.2, you can just substitute into the binomial formula for N is 20 and P is 0.2, and it happens to be 0.6296. So these are the two chances of incorrect conclusions of their test of the correct parameter P. Now, in the first place, we're okay. This is quite small, so this is the chance of getting a mistake in their testing procedure. That's all right. This one is pretty big, right? I mean, you know, I try and make this decision rule, and there's a good chance it's very wrong. So in this case, that's what we're saying. So when P is 0.2, this manufacturer has basically understated in percentage of units that need service, and the stated decision rule is used. Basically, 63% of all samples result in the manufacturer's claim being judged plausible, which is kind of unreasonable. Okay, very good. Good, okay, so that's taken us to the end of our examples on the binomial distribution. Now we're going on to the negative binomial distribution. So what I'm going to do is I'm going to give you an alternative construction to what you have in the notes. It's exactly the same. I prefer this construction. This is the one I used when I taught this course before. It's maybe more, I think it's easier to understand actually. So anyway, I'm going to tell you an alternative one. We'll go through the main lecture notes as well, but I think you'll find that this one is a little easier. So this is some notes on something called the geometric and the negative binomial distribution. So the geometric distribution is actually a precursor to the negative binomial distribution. But if you look at your lecture notes, basically the geometric comes after the negative binomial, which doesn't make any sense to me. So we're still in the world where we have a random variable x, which is discrete. And we're still in the world where we have independent and identically distributed Bernoulli trials. Okay, so this is what we have. So this is the first sentence. We consider a sequence of independent and identically distributed Bernoulli trials, and the chance that that Bernoulli trial yields success is p. Okay. Now what we're going to do in this experiment, rather than count the number of successes in a fixed number of trials, what we're going to do is define the random variable as such. So we define the random variable x as the number of trials until we see a success. Okay, so that's like saying, okay, for example, if I flip a coin which shows heads, which I suppose is a success, then with probability p, then x is the number of times I flip the coin until I get heads. Okay, so that we know that basically in this scenario, the range of support of the random variable x, so in my old version of the course I use this for the support, but you can just think that this is the range of values. So the number of times I have to flip my coin in order to obtain a success must be at least 1 to get 1 success. So that's the best case scenario. But it could be 2 times, it could be 3 times, 4 times, 5 times, and because p is non-zero, in theory I could get a huge number of times that I flip the coin. Okay, so basically in this case, basically the random variable of interest here is a positive integer. 1, 2, 3, 4, that's what I mean by that. Now let's think about what is the probability mass function of such a random variable. Okay, how you can construct this constructively. Suppose that x, we realize the value x is 1. Okay, now the probability that x is 1 is that I flip my coin and with probability p it landed heads. So the probability x is 1 must be equal to p. Seems reasonable. And that's what as I say in the explanation below. That's because we only have one Bernoulli trial and it is a success. Okay, now suppose x is 2. Now if x is 2, what must happen is, first of all, I have a failure, right? I flipped my coin, it came down tails. The probability that happens is 1 minus p. What I must do then is I flip my coin and it lands with probability heads with probability p, and that flip, don't forget, is independent of the previous one. So the probability that I get tails heads is 1 minus p times p because of the independence of the Bernoulli trials. Okay. Now, if x is 3, the probability I get x is 3 must be first time I flip the coin, I get a tail. That happens with probability 1 minus p. Second time I flip the coin, I get a tail, so that happens with probability 1 minus p. So I get 1 minus p squared. And then my third flip, I get a head, which is p. So basically, the probability x is 3 is 1 minus p squared times p. So note that there's none of this combinatorial ordering in this case. The reason being that there's only one way to get x is 3, which is 2 tails and a head. Okay, so now if I do 4, what do I get? So if the probability x is equal to 4, well, I get a tail, a tail, a tail, a head. Tail probability 1 minus p, tail probability 1 minus p, tail probability 1 minus p, head probability p. So the probability x is 4 is 1 minus p to the power 3 times p. Okay, so in general, if I ask the question, what's the probability that x is equal to x, i.e. what's the probability mass function of this random variable? Well, it's 1 minus p to the power x minus 1 times p. Okay, this is the probability mass function of this random variable. And the reason is, in order to the number of trials to achieve x successes, you have to have in a row x minus 1 failures, and then the last one is a success. So there's no combinatorial term, because there's only one way to achieve x successes. Okay, so this is so again the context is, I just repeat it one more time. The context is you have independent and identically distributed Bernoulli trials with success probability p, and x represents the number of trials up to and including the successful event. Okay, and such a random variable of such a type, with this type of probability mass function with the support 1, 2, 3, 4 off to infinity, is precisely said to have a geometric distribution. So in my old course I used this GOP. I think we use something slightly different, so you can forget about that for now. Okay, let me just say a little bit of something about this. So this is one of the very few cases where you can actually calculate the distribution function. So remember, what is the distribution function? Let's cast our mind back. The distribution function, capital F of x, is the probability that a random variable x is less than or equal to some value little x, where little x lies in the support. Okay, so what this statement says is if x lies in this sans serif x, that means if x is in the set 1, 2, 3 off to infinity, the CDF cumulative distribution function is precisely f of x is the sum over all little y's, and y must go from 1 up to x of the probability mass function. So this thing represents, this expression here represents precisely the probability that a random variable x that is geometrically distributed is less than or equal to some value little x, where little x lies in the values. It could be 1, it could be 2, it could be 3, and so on and so forth. And like I say, this is one of the few cases for discrete random variables where it can be computed. Okay, I'm just going to tell you what it is. I think this one is not so bad. I think you could be asked to do this one day in the exam. So how do you compute this how do I compute the CDF? Well, in this case, it's not so difficult. P is a constant, so I can take that outside the sum. So then I have the P times the sum y is 1 to x of 1 minus P to the power 1 minus y minus 1, excuse me. Okay, now to compute the sum of this type, okay, this sum, there is a standard formula which is called the geometric sum. So hopefully you have heard of the geometric sum. If you have not heard of the geometric sum, let me know, and I will write down a small note which states the formula explicitly. Okay, but if you do, there's an explicit algebraic expression for this thing. So what this sum is equal to the first term. The first term of this summation is 1, multiplied by 1 minus, this is called the common ratio, 1 minus p, to the power of the number of terms, x, over 1 minus this term, which is 1 minus p, which is p. Okay, this is an explicit formula, so this is not a bag of tricks that I'm using. This is a known formula for computing what I call geometric sums. So there's one reason why I call it geometric distribution, because it's all associated to geometric sums. So basically, that's the formula that I've used. Now, if you have not heard of that formula, I'm going to write it down somewhere for you. Does anybody not know the formula? There's no embarrassment to say you've never heard of it. No judgment on my side. It seems like you all heard of it, which is good. Okay, well, you can let me know by email if you don't feel comfortable. I can write it down for you. It's not a problem for me. Okay, so we've computed the sum. So the key point here is now that p over p is 1. So I get that basically the distribution function is 1 minus p to the power x. Okay, so we can compute precisely the probability that x is less than or equal to x just by using the formula that you see highlighted on the right. Okay, this is extremely useful formula. For once in our lives, we can do a CDF for discrete distributions. Okay, I'm going to show you the expectation of this random variable. This thing is a little bit complicated. You're not going to need these calculations in the exam. I'm just telling them, just showing you them because you can see why in the main lecture notes we don't have proofs. Okay, but if you like mathematics, I kind of like mathematics. It gives me something to do. So I will tell you, just show you the calculation, but don't worry again. For those of you watching on video, you don't need it for the exam. So if I wanted to compute the expectation of this random variable, how would I do that? Well, one way is just to use the definition. And you can see there are some calculation which doesn't look very pleasant. Okay, and it's not that bad, but it's not so easy if you don't know how. So I'm using this. This is the expectation of the random variable x. By definition, that's the sum over all x values. X goes from 1 up to infinity of little x, which is the random variable, multiplied by the probability mass function. Okay, so I want to compute this summation. And if you look at the summation, it's not very standard. So, for example, just in the line above, we had this summation here. And as I told you, there was a standard formula for computing this summation. For any finite x, actually it's true for any, even if x goes to infinity, it is actually this function, the summation exists. But for this formula here, there is not an obvious value of this summation. It doesn't seem to be standard, okay? But it looks like a geometric sum. So let me just show you one way which you can compute the sum, okay? So the first thing that you notice is that p is a constant in x, so I can take p outside the summation, so that's what I've done here. And what I'm left with is the sum over all x's of this term. So this is x times 1 minus p to the x minus 1. Now, the thing so the trick to notice here is that basically, if I have x times y to the x minus 1, that looks like a derivative. And that's exactly what we guess. So we get basically that term there, which I've highlighted in blue, is precisely equal to the derivative with respect to p of this term here. So if you differentiate this term with respect to p, you're going to get x times 1 minus p to the x minus 1. Okay. This is the trick to this calculation, and like I say, it's not something you will not need this in this course or the exam. I'm just showing you, just to illustrate to you why sometimes we don't do the proofs in the class. Okay, so now we are left with this formula that you see, some of it which is highlighted. Now what I'm going to tell you, and I'm not going to verify it, is if I sum over all x's and then I differentiate this in p, it's equivalent to summing this thing over x and then differentiating to b. That is to say that you can interchange the order of summation and differentiation. So that's what I've done here. Okay, and so now the formula that you're left with, you have to compute the summation inside that big bracket. Okay, that we can do using the geometric formula, and then I have to differentiate the result with respect to p. Okay, so this formula here, so this is a minus 1, I'll just leave it here. So here, in order to compute the sum to infinity, it's equal to the first term, which is 1 minus p, over 1 minus the common ratio, which is 1 minus p. So it's 1 minus p over 1 minus p, which is p. So this infinite sum here is actually equal to 1 minus p over p. Remember, it's critical that p is between 0 and 1. If it's bigger than 1, the summation does not exist, actually. Okay, so now what we're left to do is we have to find the derivative with respect to p of this expression. Okay, so I didn't spend any time doing that. I'm sure you can all do that at this level. That's not a problem for any of you. And if you do that, you get 1 over p. Okay, and that gives you the expectation of a geometric random variable with success probability p. It's 1 over p. Okay, and you can see that the expectation was painful. The second moment, i.e. to compute the variance, is even more painful, actually. So generally, one does not compute means and variances of these type of distributions using the definition. There is a way to do that using something called a moment generating function. Apparently, you don't learn that. I used to teach that, but you don't learn that in this course. So you basically don't have to worry about it. Okay, so what we're going to talk about in a moment is this negative binomial distribution. And basically, so remember that for the geometric, basically this is a collection of Bernoulli trials, and we basically keep running them until we get a success. Okay, and this is the probability mass function you can see highlighted. What we're going to do in a moment is think about the case where the number of successes you have are fixed. It's not just 1, it could be 2, it could be 3, it could be 4. And we ask the question, how many Bernoulli trials do I have to achieve to... So I'm asking the randomness associated to independent Bernoulli trials and the number of trials to achieve R successes, okay, instead of just R equal to 1, okay? And that's what the negative binomial distribution is. Okay, and I think there's a convenient time to take a brief break, so we'll just have a break for 5 minutes. We'll resume at 14:49. Okay, so let's resume. So for the second part of the lecture, we're going to talk about this negative binomial distribution. And again, like I said, I think this is a little easier way to follow or understand the derivation. We will still see the main one in the notes, but I think after seeing this, at least hopefully you'll agree with me, it's a little bit clearer than the notes. So what's the idea? So it's very similar to the geometric case. We consider a sequence of independent and identically distributed Bernoulli trials with success probability P. The same situation that we had for the geometric, except what we now measure is a random variable x, but it's not the number of trials up to and including the first successful trial. It's actually the number of trials until we see at least r successes. Well, r could be 1, 2, 3, 4. Okay, and we conclude the r successful trial. So for example, I flip a coin which shows heads with success probability p. So I keep on flipping the coin until I attain r heads. Okay, and so that's basically it, including the successful flip. Okay, so if r is 2, I flip the coin and get tail heads. That's okay, that would be the geometric, but it's not this. I get tail heads. I keep on going, maybe tails, heads. And then I stop. And the number of trials it took me to get to that second heads is the random variable which we're interested in now if r is equal to 2. So in this case, what we know is that our random variable capital X, it has to be at least r, right? Because for example, if I want r is 2, so 2 heads, I have to have at least 2 trials. I can't do any better than that. But it could be r plus 1, but I get 1 failure and r successes, or I get two failures and r successes. I'm going to r plus 2, r plus 3, r plus 4. And again, as before, because the probability of success is in 0, 1, there is a countably infinite number of trials that I could have. And of course, any realization is likely to be finite, but in practice, we don't know when it stops. Okay, so this is a random variable, and first of all, the first thing we're doing is to categorize the values of the random variable could take. Okay? Okay, so now we ask our question, what's the probability mass function? That's what this question asks here. What is the probability that x takes the value little x? Okay, now if little r is equal to 1, we know the answer. That was geometric distribution, so we have done that case. Okay, so that's why I think it's easier to start with the geometric. So if you understand the geometric, the negative binomial is slightly easier to understand. Okay, so now let's suppose r is 2, okay, because that's easier. Now what I claim is the following, and I will justify it in a moment. So now, of course, what we know is that the random variable capital X has to be at least 2, it could be 3, it could be 4, so on and so forth. And I claim that the probability mass function, I'm going to use this notation here today, is equal to x minus 1 times 1 minus p to the x minus 2 times p squared. Okay, and so the question is, why is that the case? Okay, well, the reason it's the case is the following. I know that I'm going to have 2 successes, and I'm then going to have x minus 2 failures. That has to be the case, right? And x is at least r. Right? So r is at least 2, and r is 2. So I've got 2 successes and x minus 2 failures. So these are independent and identically distributed Bernoulli trials. So I know that my last trial, I get a success, because I stop once I get my second success. Okay. Right, and then basically we know the last successful trial is at x, so the first successful trial lies in one of the other x minus 1 positions. Okay, so what that means to say is there are x minus 1 ways where the first success could appear. So for example, let's say r is 2, so I flip the coin, first time I get a heads, p, with probability p. Then if I realize, let's say x is 4, I'll get tail, head. Okay, so that's my 4 trials. Okay, but the probability that I get 4 trials could be another way. I could get tails, head, or I could get tails, tail, head, head. Okay, so that's 3 ways, x minus 1 ways of doing it. So this basically, this term here comes from the fact that the other success could have landed anywhere in those remaining x minus 1 trials. So that's why we multiplied by x minus 1. So recall, just to make it clear, this only occurs if the trials are identical. If the trials are different, then there's something else going on, but we don't think about that in this case. Identical trials. Okay, so that's the probability mass function if I have only 2 successes, and it should look very familiar to you because it looks very much like the geometric case, okay? In fact, if well, yes, it looks like the geometric case. Now, let's look about the case r is equal to 3. Okay, so r is equal to 3. I flip my coin until I get 3 heads. Okay, so we know that the number of trials in order to achieve at least 3 heads must be 3. It could be 4, it could be 5, and so on and so forth. And I claim that the probability mass function in this case is going to be x minus 1 choose 2 times 1 minus p to the x minus 3 times p cubed. Okay, so let's think about this. Obviously, it looks like a horrible monstrosity, but let's try to understand where this came from. So we know as follows, as before, we got p to the power 3 successes, and so the number of times we failed is 1 minus p to the x minus 3. So remember, x is at least 3, so this term is making sense. Okay, so that's the chance of a particular realization of this. So as before, we know that we have to have the last Bernoulli trial is successful, so it's a heads in my example. Okay. So then basically what we have is we have the first and second successful trials must lie in one of the first x minus 1 trials. Okay. So basically there are so what I'm going to do is I've got x minus 1 things, and I want to take 2 of them away. And we know the number of ways you can take 2 from x minus 1 is x minus 1 choose 2. Okay. X minus 1 is positive, by the way, because x is at least 3. And x minus 1 is at least 2, because 3 minus 1 is 2. Okay. So basically there are x minus 1 choose x minus 1 choose 2 possible ways of getting 2 successes in the first x minus 1 trials. Okay, and there's only one way you can get the final trial as being a success. So again, this is coming from the fact that you've got to have x minus 3 failures. Here you've got to have 3 successes, and this is coming from the fact that you've got the identical trials, and that those first two successes must come in those first x minus 1 trials, and the probability of each of those are identical. Okay, so this is now looking kind of like a nice formula. We're going to try to think about it when r is equal to 4. Okay, so you can see the general one at the bottom. Let's think about r is equal to 4. So if r is equal to 4, now what we would have is we'd have 1 minus p, x to the minus 4 times p to the 4. Okay, that's the same logic. I get 4 successes, I get x minus 4 failures. Okay, so I have p to the 4, 1 minus p to the x minus 4. X is in the set 4, 5, 6, 7. Okay, now what do I have? Well, now what I must have is I've got now 3 successes which happen in the first x minus 1 trials. Okay, and basically so what we're going to do, we want to take 3 from x minus 1. Okay, so basically in this case, 3 from x minus 1, when we don't care about the ordering, is x minus 1 choose 3. So the probability mass function when r is equal to 4 would be x minus 1 choose 3, 1 minus p, x minus 4 times p to the 4. Okay, now if you keep on doing that, you can do r is 5, 6, 7, 8, 9, 10. Basically the formula is going to be basically the case that for any r at least 1, the formula for the probability mass function x minus 1, that's what we had here, choose r minus 1, here r was 3, 1 minus p to the x minus r, because that's the number of failures that you must have, and p to the r is the number of successes. And x, the random variable, must lie in the set r plus 1 off to infinity. And any probability mass function which has this functional form and this support is said to have a negative binomial distribution, and the parameters are r and p. Okay, so remember in the binomial case, right, what we had, remember if there's a formula here somewhere, the binomial case, sorry, Let me go there. Binomial. Right, if n choose x, p to the x1 minus p to n minus x. So n is fixed, and x is the randomness, random variable, and p is the parameter. Okay, so in this case, x is the randomness, r and p are fixed. Okay, just a way, and maybe if you want to, if you think of trying to memorize this type of formula, there's no reason to do so. That would be what the kind of difference that should be in your head. But fundamentally, the binomial and the negative binomial distribution are both associated to independent and identically distributed Bernoulli trials, but they measure different things. So if x is a binomial random variable, you know the number of trials that you have, and you count the number of successes in those number of trials, and you work out the probability that that occurs. In the negative binomial case, what you have is you know the number of successes you want to get, and then you count the number of trials to achieve this success. And that's what the probability mass function that you see written here represents. So they are associated to the same things, but they do different things. Okay. Okay, just a couple of remarks before we go to the main lecture note. Well, the distribution function, so for the geometric it was nice, for the negative binomial it is not simply, it's not easy to write down, and typically you don't get an analytic expression unless you have some special cases. I mean, R is 1 is the case of the geometric, so you've got it. The expectation, if you want to get the expectation from the definition, is very tedious. You saw this one, and even if you're happy with this calculation, then what you will have in the case of the negative binomial, you'll have some negative binomial coefficient in there, is really painful. I would not waste my time trying to do it yourself unless you like spending time doing calculations. You're not going to learn anything either, actually. The way to do these, calculate the moments, the moment of this, the expectations we're going to see later is going to be R over P. Okay, and the way to do that again is using this moment generating function, which unfortunately we don't teach you. So just to tell you, I mean, if you want to find out about these things, you're not going to be examined on it. Okay, so that's my explanation, but we can look at the lecture notes because they are also what we're learning from. So let's have a look at this, and if this alternative thing expression, this alternative description is better for you, then that's fine. I don't mind. I just like the other one. It's the same. I mean, I'm just going to repeat myself, but anyway. So let us consider the case. You have properties are the same as the listed before. You have Bernoulli trials, independent, identically distributed, and we keep on doing that until a fixed number of successes occur. You can see that it's less constructive here. So then what we are interested in is the probability of, I was using R, this is K, it's the same thing. The probability of the kth success occurs in X trials, where X is now a random variable. And this is very nice, it just, it just summarizes the difference between the binomial and the negative binomial. So this is the binomial, this is the negative binomial. Okay. So again, this is another way of doing it. So again, you can think of it this way. So suppose you want to find the probability that the fifth success occurs in 7 trials. Okay, so we have to have 4 trials in the first 6 and a success in the last time. So that's, for example, if you prefer like this, SSFSFSS or something else. So the probability of getting this sequence is p to the power 5 times 1 minus p squared. Okay, where p is the probability of success, and the number of all possible sequences is 6 choose 4, because as I said, the 7th trial is a success. Okay, so this is just another way of explaining what I just told you. All right, if you like this better, that's definitely okay. We're just trying to convey the idea. So basically, if x is a random variable that represents the number of trials to produce 5 successes in a sequence of independent Bernoulli trials, then, for example, the probability that x is equal to 7, as we said, is 6 choose 4 times p to the power 5 times q squared. That's what we said already. Okay, so in general, as we have said, so again, that's why I spent more time. I think this gets very fast to the conclusion, whereas I think it takes a lot longer to think about it. So if we suppose x is a random variable, it's the number of trials to produce k successes in a sequence of independent and identically distributed Bernoulli trials of success probability p. The random variable x is said to have a negative binomial distribution, and the two parameters are k, the number of successes, and p, the success probability of the Bernoulli trial, and this is the probability mass function. Okay, and this is exactly what we've just said. Q is equal to 1 minus p, and it's the same formula I just gave you, except he uses k and I used r, and it doesn't matter whether you use that, whichever you want. And remember that the support starts, you have to have at least the number of successful trials or more for the random variable. So that's a negative binomial distribution, and it can be shown, and again, it's quite difficult to do that from the definition. And in fact, like I said, the nicest way to do that is using these generating functions, which we don't learn. But you can show that the expectation of this random variable is k, the number of successes over the success probability, and the variance is of the order 1 minus p times k over p squared. Okay. Again, I'm happy to derive these formula, but this one, it seems, is going to be a lot more work than the binomial was. I don't mind it, but I don't think it's that important. So there are some examples. Actually, this one, the first one, is for the first time in a while very interesting for me, a little bit. So you have an NBA championship series. That means basically you are in the Eastern or the Western Conference final, or in the NBA championship itself. And if you win 4 out of 7, you are the champion of the East, the West, or the NBA in total. And normally that's just the Golden State Warriors, but never mind. So suppose that team A and B face each other in this championship game, and the team A has a chance of winning a given game with probability 0.55 over game B. Okay, so the idea here is that each game is going to represent an independent Bernoulli trial with success probability P. Okay, and it's not, I don't think it's so reasonable in this example, because of course there is some correlation or dependence. But if you won the first game 1, then there's some impact that you might win game 2, but that doesn't matter. We'll just suppose it's independent. So we ask ourselves the question, we ask the 2 questions. What's the probability that team A will win the series in 6 games? And we'll think about part B in a moment, right? So the probability that team A will win the series in 6 games is basically the chance, is basically modeled in the same way, in the following way, sorry. So X is the number of games that team A plays to win the series. And the probability that team A winning a given game is 0.55, and it's not therefore, you have to make an assumption, like I said earlier. We're assuming that each game, the win or loss, is independent of the other, and you know, that's an assumption. So it's not necessarily therefore. And we assume now that X follows a negative binomial distribution. So the number of successes that they need are 4. Okay, so once they've won 4 games, they've won the championship, and the chance that they win each game is 0.55. So the assumption is that the random variable x, the number of games that the team A has to play in order to win the championship series, it's 4, and the success probability is 0.55. Okay, this is actually a nice example. I like this one. So the first one says, what's the chance that team A wins in 6 games? Okay. So the chance that they win in 6 games is just basically you substitute the case x is equal to 6 into a negative binomial distribution with r is 4 and p is 0.55. So you can see the formula there. Actually, I suppose it's not too far what they probably do in analytics in the NBA or something like that. So that's why it's interesting. Part B. So part B says, what's the chance or the probability that team A will win the series? Okay, so this is a bit different because we want to know the chance that they win, the probability that x is at least 4. Okay, so the probability that x is at least 4 is the probability that x is 4 plus the x is 5 plus x is 6 plus x is 7. Okay, that's basically the chance they win the series. They have to win at least 4 games. So you're just substituting x is 4 into a negative binomial with 4 and 0.55. X is 5 when k is equal to 4 and 0.55 and so on and so forth. So you can see the formula. We're just substituting numbers into formula, and if you do that, apparently the answer is 0.6083. Okay, I suppose you could use this model for other things rather than analytics. Okay, let's take a look at example 2. So example 2 is the following. So you have a busy time, a telephone exchange is very near capacity. So callers have difficulty placing their calls. It may be of interest to know the number of attempts necessary in order to make a connection. Okay. So basically, we suppose the chance that your call is not connected, the chance of connection during a busy time is 0.05. And we're interested to know the probability that 5 attempts are necessary for a successful call. So again, we are in a negative binomial context. That should be clear. The number of trials that are required to have the first success, okay, is known to have a special case of the negative binomial distribution, and that's the geometric. Okay, well, we know that already. We have learned that, which is good. So let x be the number of attempts necessary to obtain the successful call. So the probability of connecting is 0.05. So this is just a negative binomial case where r is equal to 1 and p is equal to 0.05. Okay, it's a geometric distribution where basically you don't have to compute. So then basically you have this negative binomial distribution of geometric 0.05. It's the same thing, okay, because this one you're really interested in the first time, not the second time or third time. So the probability you take 5 calls is just basically equal to 0.05 multiplied by 0.95 to the power 4. Okay, the combinatorial term is 1 in this case. So it's just the geometric. Okay, that's why I liked to construct it. Okay, so that's that. So those was the negative binomial distribution and the binomial distribution. And we're now moving on to something else. It's called the Poisson distribution. I'm going to talk a little bit about this, and I probably won't get too far into it because I don't want to say too much right now. In fact, the Poisson distribution comes from the theory of stochastic processes. So just in case you're interested, in fact, we're going to give you the distribution, but the actual thing comes as a byproduct of defining stochastic processes in continuous time. But this, unfortunately, is beyond our capabilities today. But those of you who are interested, you will may one day see how you get a Poisson distribution. So it's a byproduct of developing a stochastic process, but in fact it turns out to be useful for modeling things. So this is the idea. So you have experiments yielding numerical values of a random variable x is basically the number of successes occurring in a given time or in a specified region are called. Okay, so basically what this thing is, it's like you can think of it, you have an interval of time. What the Poisson distribution occurs is a byproduct. It counts the number of events that occur in this time interval. That's really where it comes from. And this is what it says. Time interval is the easiest way to think about it. So let's say you have an interval of time 0 to t, and under some mathematical conditions, the distribution of the number of events which occur in this time, okay, happens to be Poisson distributed. And this is what's called it's called a Poisson experiment. So the interval of time or the region, okay, there's a two-dimensional Poisson process, doesn't matter about that. But in a given interval of time, the interval time t is arbitrary. Okay, so this is basically the origins. What we're going to see in this lecture course is actually just a probability mass function. So I think that this interpretation doesn't necessarily help us at this stage, but it tells you something about this. Okay, so let's think about this. I mean, I'm going to read this out, even if I'm not completely agreeing is the way to derive this distribution. So a Poisson experiment, it generates observations of this random variable x, and it represents, for example, the number of telephone calls in an hour, or the number of postponed games due to rain during a football season. I don't know if that happens anymore, but it used to happen when I was a kid, but maybe not now. Definitely not in Europe anyway. And the specified region, if you want to think of it as a region, could be a line segment, an area, a volume. So it's hard to kind of describe this thing non-mathematically without being mathematical. So that's why I don't like this thing. But so, for example, it could be mushrooms on a plot of land, number of bacteria in a given culture, the number of typing errors in a page. So, again, I don't know if you get. I don't know how you get anything out of this, really. But anyway, let me just say, we are going to get something interesting out of it at the end, but this is not necessarily the best thing to do. So a Poisson experiment, if you like, possesses the following properties. Okay, This is really the way to write down a Poisson process. So the number of successes occurring in a time interval are independent of those occurring in any other disjoint time interval. Okay, so this is a nice way to write down something called independent increments of a stochastic process. Again, I don't think you learn anything out of this. The probability of single success during a short time interval is proportional to the length of the time of the interval. And the size of the region, and it doesn't depend on the number of successes occurring outside the interval or region. Okay, and this is basically described I don't know. Anyway, the probability of more than one success occurring in a short time interval is basically zero. Okay, negligible. These are the three. So again, for those of you who do go on to learn stochastic processes, you'll see these properties 1, 2, and 3, and you'll see a mathematical description of these. But it's more interesting. This, I think, if it were my notes, I would have started here. Okay. So this, if you like, you can read over those notes. But I highly recommend those of you who are really interested in this thing, Poisson experiment, to read about Poisson processes, and then you will get something out of it. But I don't think that helps. And it's not a criticism of my colleague. I just think it's a hard thing to describe without mathematics. Okay. So this is where I think is the nice place to start. So if you denote the number of successes in a Poisson experiment, it's called a Poisson random variable. Okay, this is correct, in fact. The probability distribution of such a random variable x is defined as follows. Okay, so if you take one thing from what I've said in this section, it's basically that this is the thing. So you take a parameter lambda. Okay, lambda is positive. It's a number. It could be 0.01. It could be 10 million, but it's a positive number. And the probability mass function for this random variable, which corresponds to the number of successes in this Poisson experiment, has this following form. So it's e to the minus lambda to the power x over x factorial. The support of the random variable is 0, 1, 2, 3, 4, so on and so forth. Okay, so lambda, it says, is the average number of successes. We're going to rigorously show that in a moment. And e is, of course, the exponential 2.712, basically. Okay, so I'm sure you know what that is. I don't think you need to know. Okay, now, if you ask the question, is this a probability mass function? Of course, it's a non-negative function. So I substitute any x which is in the set 0, 1, 2, 3, and of course I get back something that's non-negative. So that's good. The reason that this thing will sum to 1 is basically because lambda to the x over x factorial, if I sum from x is 0 to infinity, that's the Taylor series expansion for an exponential function. So e to the x, if you like, is defined to be 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial plus dot dot dot. Okay, so that's why this thing sums to 1. Okay, it's actually some nice. If you know what I'm sure you know what a Taylor series expansion. That's the reason why it sums to 1. And this is how the probability mass function looks for different values of the parameter x, lambda, excuse me. So if lambda is 1, you can see that we said that lambda is the average value of this random variable. It happens to be the mean. So you see basically a peak of this mass function around 1 in this case. You would expect that the average value to be having a lot of probability around it. So similarly, if x is Poisson 4, then you see a lot of probability around 4. If x is 9, you see a lot of probability around 9. It doesn't necessarily, this modal value, we call the peak of this curve the mode, and it's not necessarily the mode, but it is the average value. So basically, what am I trying to say? I'm trying to say the value of the parameter lambda intrinsically affects the shape of the associated probability mass function. So different lambda give you different shapes, and they give you different types of data which you can well represent, or different types of variables which you can well represent. Okay. So what we're going to finish with this theorem today. We've got quite a lot of time, but it won't take us very long to prove it. So we might finish a little bit early, but I think we're going fast, so it's all right. So the theorem is that if x is Poisson distributed, and there's a parameter lambda, then we can compute its mean and its variance. So its mean, its expectation is lambda, and that's the same as its variance. Okay, and we proved this one. This one is quite nice. Okay. So we start with the expectation of x. So the expectation of x, by definition, is the sum over all x values. X goes from 0 to infinity in this case, of little x times the probability mass function. Okay. Now, what do you note about the expression that's written here on your on the right-hand side? Well, if little x here is equal to 0, of course, this summoned, the expression in the sum is 0. So the sum doesn't go from 0 to infinity, it goes from 1 to infinity. Okay, that's the first thing you notice. And then the second thing you notice, if you do x over x factorial, remember x factorial is x times x minus 1 times x minus 2 dot dot times 1. So x over x factorial is precisely x minus 1 factorial. Okay. Very good. So we're almost done. It doesn't look very obvious that we're almost done. But the key point is that basically, as I mentioned to you a moment ago, essentially what is characteristic of this probability mass function is the fact that it's intrinsically linked to the Taylor series expansion of an exponential. So what I'm going to do, so you know that e to the minus lambda, that's a constant, so I never care about that, I can take it outside. And you have the sum x is 1 to infinity of lambda to the x over x minus 1 factorial. It looks very much like the Taylor series expansion for a exponential function, but not quite. And there are two things which are missing. First of all, I'd like to have lambda to the power x minus 1. And the second thing I'd like to have is I'd like going not from 1 to infinity, but from 0 to infinity. So what I can do, although he doesn't do it explicitly, I can take e to the minus lambda outside. He doesn't do that. You can leave it there. It doesn't make any difference. Lambda to the x times is equal to lambda to the x minus 1 times lambda to the x. So I can take that one of those lambdas out. And then what I'm left with is lambda to the x minus 1 over x minus 1 factorial. Okay, well it still looks better, but it's not going, the summation is going from 1 to infinity. So if I make the substitution y is equal to x minus 1, then if x is equal to 1, y is equal to 0. If x is equal to 2, y is equal to 1, so on and so forth. So if I make that change of variable in the summation, I go now from y is equal 0 to infinity. Now, lambda I've taken outside the sum, e to the minus lambda is there, and I've lambda to the power y over y factorial. And now I'm in a good situation. Why am I in a good situation? Because now if I exclude this, if I take this term here outside, e to the minus lambda, outside the summation, I have the sum y is 0 to infinity of lambda to the y over y factorial. That summation is precisely e to the power lambda. So then I have e to the minus lambda times e to the lambda, which is equal to 1. And so that is why I get lambda here. Okay? So that's why the mean or the expectation of a Poisson random variable is precisely lambda. Okay? Is that clear, or is there, do people know that, I'm sure you know the Taylor series expansion for the exponential. Again, if you don't know anything or you don't not understand something, you can send me an email and I can write down very explicitly the calculation. Okay, there's some missing steps here. So that's the expectation of x, and again, you're very welcome to ask questions if you're not clear. Okay, now if I want to compute the variance, right, I mean, there's a couple of ways of doing this. He's going to do it the easy way. There's not necessarily anything wrong with doing it the easy way. So there's a trick here. So the trick he's going to do is he's going to compute the expectation of x times x minus 1. Okay, because it turns out computing that's quite nice, and you can get then from at the variance. So let's think about computing the value of the expected value, excuse me, of x times x minus 1, and then we'll try and understand why that's useful. Okay, so the expected value of x times x minus 1 is the sum over all x's, x goes from 0 to infinity, of x times x minus 1, that's my function, multiplied by my probability mass function. Okay. So that's by definition. We're not doing anything too clever there. Now, if x is equal to 0, the sum under 0, right? Because if x is 0, 0 times minus 1 times this is 0. If x is equal to 1, well, this is okay. 1 minus 1 is 0, and this is some number. So basically, this summation doesn't start from 0, it starts from 2. So I have the sum x is equal to 2 to infinity of e to the minus lambda over lambda to the x, x minus 2 factorial. Okay. Now the trick here is going to be exactly the same. What I want to do is I want to convert the summation you see on the right of the page, and I want to convert that into something like lambda to the power x over x factorial. The sum from x is 0 to infinity. How can you achieve that? It's a very similar trick to before. You to make the substitution now, y is equal to x minus 2. So if y is equal to x minus 2, obviously here I get lambda to the power y plus 2 over y factorial, e to the minus lambda stays. The sum goes from 0 to infinity. Okay, so that's where the lambda square has come from. E to the minus lambda never changes. That's always there. I get lambda to the y over y factorial. So again, for the same reason as when we computed the mean, we get lambda squared, e to the minus lambda multiplied by the sum y is 0 to infinity, lambda to the y over y factorial. That sum is precisely e to the power lambda. E to the power lambda times e to the minus lambda is 1, so I get lambda squared. Okay, so that's this quantity. But you'll say, well, so what? How do I compute the variance? Well, you can compute the variance using the following formula. So this is what we just did. I don't know why that's repeated. So the variance of x happens to be equal to the expected value of x minus multiplied by x minus 1 plus the expected value of x minus the expected value of x all squared. And you say, where does this formula come from? Well, remember that the variance of x is the expectation of the square of the random variable minus the expectation of the random variable all squared. So this expression here, that's just coming from the definition. So I haven't touched that, or he hasn't touched that. Now, to get the expected value of x squared, well, I have the expected value of x times x minus 1. So this expression here is equal to the expectation of the random variable squared minus the expectation of the random variable. Okay? Because basically if I do the expected value of x squared minus the expected value of x, and then if I add the expected value of x on, this term here, sorry, get it right. This term here is equal to the expected value of the random variable squared. Okay. So that, what does that mean? Well, that means that basically the variance of x is equal to this formula. Okay, now can we complete the calculation, please? Is the question you might want to ask. We can. The expected value of x times x minus 1, we verified that was lambda squared. So I have lambda squared here. The expected value of x we verified was lambda. The expected value of x all squared is lambda squared. So I have lambda squared plus lambda minus lambda squared is equal to lambda. So the variance is equal to the mean. Okay. Maybe I'll just say. So basically, in conclusion, the same thing. The point is the Poisson distribution is a positive random variable which is 0, 1, 2, 3, 4 off to infinity. It has finite mean and finite variance, and its mean and variances are equal. So if you specify the parameter, you immediately specify the mean and the variance. There's only one parameter for that. Okay, very good. Maybe. I think we can leave the examples. I think it's we're really far ahead of the rest of the classes, so I think we'll look at the examples on Thursday of next week. So thanks very much for your attention, and I'll see you Thursday. Thank you.